You can now build your own neural networks. This video will highlight some final points to consider when building such networks. It is important to realize that neural networks are not 100% accurate. In reality, neither are we. For example, can you always read someone else's handwriting? Aiming to achieve over 90% accuracy is a good target to aim for. If 100% performance is critical to operation, for example, you do not want an autonomous car to run over people 10% of the time, then be sure to include contingency into your designs. For example, you could use AI to navigate a car, but have ultrasonic sensors on the front of the car to immediately override the AI and stop the car if an object is detected in front of it. There are several questions you need to consider when building a neural network. What network type should I use? What options in the network and in the training process should I select? How do I know if my network is working correctly? How much data should I use, and how do I make sure my network is not overfitting? Probably the most difficult place to start is knowing what architecture to use, for example, numbers of layers, etc. You will need to have a lot of experience with neural networks to know what works best for a specific application. When starting out, which is what we are doing here, it is best to build on the knowledge of others. If you know a particular network performs well for a particular application, use this as your starting point. So, for example, if I wanted to build a neural network to recognize letters of the alphabet, our digit recognition neural network seems to be an appropriate place to start. All we need to do is to give it a new set of training data. There are lots of proven networks out there that have already been trained. GoogleNet and AlexNet are two common ones for recognizing objects. Pre-trained networks also have the advantage that if you train them on new data, the training process is quicker, as the starting point for training will already be located close to optimum values. The one downside to this is you are fixed by the input size of the network, although there is nothing stopping you using the architecture, but modifying it for your own needs. Also check for publications in AI. These papers will give you details on what networks they used for their specific applications. There are also lots of options for layers in your network. For example, if you use a dropout layer, what percentage of dropout should you use? Training also gives you a lot of options to try, for example, the initial step size. To begin with, you should try the default values, and then modify after that to see if your network performance improves. MATLAB comes with a useful app called Experiment Manager, in which you can try out different parameters with different values. All it is essentially doing is running the training multiple times, with the different sets of parameters you have picked to investigate. You could do this yourself, keep changing parameters and retraining to see what gives the best results. The advantage of using Experiment Manager is that you can set up all the values you want to investigate, and then leave the program running, for example over the weekend. You can then check all the results first thing Monday morning. Although 100% training accuracy sounds good, you also need validation accuracy to be as high as the training accuracy. This demonstrates the network is not only trained for specific data, but for all data in general. The loss value should also be low. A high loss value is an indicator of when the network is not working well. Once you are happy with your network, check your network is performing well in its application, to ensure it is working as required. You cannot supply all the possible variations in data, which is over 800 billion for GoogleNet. But you do need a sufficient amount of data for your network size. If you are getting 100% accuracy during training, but not for validation, then you are probably overfitting. Here are a few points for considering if you have enough data. First option is to collect a lot of data, which can be a time-consuming option. Second option, which is the one most commonly used, is to use data stores for your training data. For example, GoogleNet is trained on thousands of images of objects. These objects are saved in data stores which you can access and use to train your own networks on. The term big data is now commonly used, and it encourages researchers to save all their data from their research and allow access for other researchers. This makes it ideal for training data for AI. As an example, imagine a hospital wanted to develop a neural network to recognize lung cancer in an X-ray image. The hospital may have 1,000 images from its patients. However, if every hospital in the world saved its images in accessible data stores, the developer of the neural network would then have millions of images to train the network on. Thus, as a researcher, it is important to not only save data, but to make it accessible and to use it whenever possible. In some cases, you can simulate data. For example, you could use a camera on a robot in WebBots to take lots of images of an object from various angles, for example, a table. You can then use these images in your network training. As this is from a simulation, you can leave the simulation running for as long as is required to get enough data. One final option is to create your own data from existing data. Take our digit recognition problem as an example. If we did not have the stored dataset, we would have to write out each digit 1,000 times to get the dataset we required. However, in the example here we have just written out the number 2 5 times, giving us 5 pieces of data. What we can do, using a MATLAB program, is rotate each one of these images to 5 different orientations, thereby giving us 25 images. We can then resize each of these 25 images, again simply by using a few MATLAB commands, to 5 different sizes, giving us a total of 125 images. Thus, we have quickly produced 125 images from our starting 5 images. All this data is valid, as it helps the network to recognize writing of different sizes and orientations. However, you do need to make sure you have enough variation in the data to account for the possible variation the network may encounter. For example, the network did get a little confused between the numbers 3 and 8, so you may want more handwritten examples of these cases. Overfitting is when the neural network can exactly predict the output for each piece of input data, i.e. it is 100% accurate. The problem arises because there is not enough training data. Imagine we have a network with 1,000 internal weightings, but we only give it 10 pieces of data to train on. The network may only need to set 100 of its weightings to get the correct answer for the training data, leaving the other 900 weightings as random values. Now, if you input a new set of data, then these random values may get used and therefore predict the wrong output. What you need is either enough data so that the network cannot fit all of it, or a simpler network with fewer connections for the problem. This forces the network to train for the best option solution rather than a perfect solution, and enables the network to work for a general rather than a specific set of data. The commonest way to identify overfitting is when training accuracy is high, but validation is low. The easiest option to avoid overfitting is to make sure you have plenty of data for your network size. Another approach, shown to be successful, is to use dropout. When the network is training, a dropout layer will randomly deselect inputs, effectively setting them to 0. This random selection changes for each training cycle. This forces other weightings in the network to be set accordingly to obtain the correct output. In this way, no weighting is left as a random value. At some point in the iteration of training cycles, each has been forced towards some optimum value. This helps the network towards more generalized recognition. This session has been a brief introduction to neural networks. If you wish to learn more, the best approach is having a go at developing your own networks for your own applications. MATLAB run excellent free online courses on its products, including deep learning, and this is a good place to continue your journey into understanding AI. We will not try to implement neural networks into our WebBots models for this module, but if you wish to explore this route, there are a few options. MATLAB has a C++ code generator, so you could convert your MATLAB neural network into C code to run on WebBots. You can also use MATLAB as the programming language in WebBots, which is not something we do in this module, but is an option and would enable you to use the MATLAB neural network directly in a WebBot simulation. You could also totally ignore MATLAB for generating your neural network and develop your own network in whatever language you wish. To summarize today's session, artificial intelligence is a powerful technique, and it has gained a lot of interest over the last decade. You must use an appropriate neural network architecture for the problem you are addressing, and be careful to ensure you have appropriate datasets for training. Neural networks are not 100% accurate because of their generalization feature, although they can and do work very well. However, depending on the application, always consider backup alternatives in cases where a wrong AI decision can lead to problems. AI will impact on our lives in many ways, and it is important as an engineer to be able to understand its capabilities and be able to apply it in a safe and practical way.